Okay, let us start our this is fourth lecture today, but you already should have lecture notes for fifth lecture, just in case if we have time to already. I hope that we will have a possibility to go slightly faster, especially because we already were exposed in some sense to the calculation of to one way of calculating main quantity, which I want to address today. So let me remind you that we developed more or less the tools of dealing with positive product of characteristic polynomials or spectral determinants, then a product of their inverse determinants, and now, by the reason that is apparent, we'd like to develop methods of calculating expectation values of ratios of determinants with different spectral parameters. And this is just to remind you how, for example, one can extract the mean spectral densities, density of eigenvalues, from such an object. We should take this object, differentiate it over parameter t, entering here. So spectral parameter here is written in the form z plus t, whereas it's just z in the denominator. So for t equal 1, we would have just 1 by definition here. But if we are able to calculate it for arbitrary value of z and t, then we can extract using this identity, just trace of the resolvent. I demonstrated last time how it appears if it's not evident from here. And in fact, we had a lecture by Margarita who showed us how to do it using simultaneous integration over commuting and anti-commuting variables. I will go the same route, but actually we'll do it differently. So you will have two different perspectives. I will do it more in line with our previous consideration. So as you understand, we need tools to deal simultaneously with commuting and anti-commuting variables. So these rules, let me just formulate these rules and explain the most important of them. It's frequently referred to as supercalculus. So let us suppose that we have a vector phi, this is our notation used in this lecture, with n complex commuting components, just n component vector with usual type, and its counterpart psi with anti-commuting components. So let us arrange them into a single vector or object, supervector, which in fact I will always think as a column of two capital N numbers. First half are just commuting numbers forming vector phi, and then follows anti-commuting components of psi. I also will use the notation which will enter all our main expression. I just use this kind of scalar product, which is sum of two objects that we already encountered before. So we will look at this as corresponding scalar product. And we also need a notion of supermatrix in the same way as supervector is basically two-component object in a sense. First half corresponding to commuting and second half, bottom half, to anti-commuting entries. It's natural that supermatrix will have 4 blocks, and diagonal blocks they are entries which are G-even or commuting entries. Either they are just, in some cases, particular case, they can be just usual complex numbers, but in general, they may have nilpotent parts, so-called nilpotent parts, just made of product of even number of various Grassmannians. So they are J-even elements of our algebra. So as I discussed, A and B just matrices with commuting entries, but sigma and rho of diagonal entries, they are these entries of these matrices are just anti-commuting Grassmann variables or G-odd components of our algebra. Now, basically, this is what I introduced to you. It's kind of vocabulary that we use to deal efficiently with these objects and write corresponding, for example, Gaussian integrals and then non-Gaussian integrals with respect to the supervectors in the same way as we did for only commuting or only anti-commuting variables. So supermatrix with this block structure, so these blocks are all n by n matrices. It's in this composition just decomposition just induced by the corresponding decomposition of our supervector. So this matrix supermatrices of this type, they act on supervectors in the usual sense. It's just if you take M of this form and multiply it with phi of this form, by usual rules of multiplying matrices and matrix with a vector from the right, you will see that the result will be again supervector with the same essential structure, namely that its top n components will be even elements, although, as you immediately see, they may involve parts which are made of products of Grassmann variables, and bottom half. So here we have n commuting components, and the bottom half will be made of Grassmannians or anti-commuting odd elements, as it obvious from the fact that we multiply, for example, here rho, which is made of Grassmannians, with phi, which is made of usual commuting numbers. And here we multiply B, which is made of usual, with no, maybe not usual, but at least commuting entries, with psi, which is made of Grassmannians. We can build scalar product of phi with m phi, and by this we understand the following natural object, which this just follows from m acting on phi. Sometimes it's convenient to have matrix transposition defined for various goals, and in order to preserve the property that natural property that matrix M multiplied with phi transposed is equal to phi transposed M transposed, one, just using this as a definition, one notice that you see here there is a small subtlety that find components of phi and M change places, and we know that this for Grassmann for anti-commuting numbers this may involve change change of sign in front. So if you may just check that definition of transposition, which follows from this simple rule, is as follows. You should transpose matrix A, transpose matrix B, put in this upper right corner transposed row, and the only change that you put here transpose sigma. Here you put this is very natural, but you put minus sign in front. As I mentioned last time, sometimes one introduces this operator or this involution. We do not need it, in fact, but using this involution, you can formally define what is Hermitian conjugate, but just in usual way. But I stress it for Martin, we won't use it anyway, just by the fact that it's frequently or quite frequently encountered in the literature, so people should know. Mm-hmm.
Can you help me understand the product of two supermatrices?
Yes. Product of supermatrix is supermatrix, and you build it using conventional rule of multiplication of matrices.
But you don't get a mixture of...
Mixture of what?
Mixture of both commuting and anti-commuting.
But you will have, if you just take two supermatrices and multiply them, you will have in the end precisely the same structure. Those entries which are on diagonal. Let us try for the simplest possible example. So we have A, B, sigma rho, A tilde, sigma tilde, rho tilde B. So in this block, so it will be again A plus sigma rho tilde. So you see, because we take sigma times rho tilde, this contains product of even number. So this will be then commuting entry, no problem. What will be here? A commuting times sigma tilde anti-commuting, so anti-commuting, and will be again anti-commuting. So the structure is preserved by this multiplication. So you can multiply them as usual matrices. No problem. This structure is preserved. Okay. So as I mentioned, one can define Hermitian conjugation just as transposition and then involution taken, but I won't need it. Really fundamental role in everything which deals with in all operations, all non-trivial operations within the supercalculus is played by two most important objects, in fact related. One is supertrace, which is generalization of usual trace, and second is superdeterminant. And here are just definitions. Supertrace, we have this structure of matrix M. So supertrace is simple. It's just trace of A minus trace of B. This is an important difference from usual case, case of usual matrices, where if we had decomposition, block decomposition, we would have just usual traces, sum of traces. Here we have this difference of traces. And now, even more complicated looking notion of superdeterminant, which is there are two, in fact, equivalent formulas for superdeterminant. I had an idea just to present one, because second, I will write it on the board in the moment. I just wondered why to give two, but Martin persuaded me to give both because he found recently quite an interesting exploitation of if you know that there are simultaneously two different ways one can exploit it. I won't show you this example, but I just show you that for your information that superdeterminant of M, and this is also an exercise to show that basically it can be also written as determinant of A minus sigma B inverse rho divided by del B. This is second formula. It's completely equivalent to this one, although it's not immediate to see, but try to prove it. And sometimes it's useful to know that one can represent superdeterminant in two different ways. So but basically look at these two notions as definitions. And important exercise is to satisfy that with this definition, one has natural extension of usual most important properties of operation of taking trace and taking determinant to the case of supermatrices. Namely, what is the most important property of, I believe, of the trace? That it's taken under, for usual matrices, under trace, you can make a cyclic permutation of matrices. And this follows from the property that for usual matrices, trace of product of two matrices is independent of the order in which you take these two matrices. Here, you see, it's just, we know that even for usual matrices, they do not commute, or they only commute on the sign of trace. For matrices involving odd or Grassmann variables, we know that changing something places could easily give rise to extra signs. So everything is taken care of coherently to preserve this property for supertrace. Namely, precisely this minus sign allows one to prove that supertrace of product of two is the same object irrespective of the order in which you take two. And of course, then you immediately extend it to the cyclic permutation of more than of many matrices. Now, what is the most, I don't know, again, it depends on point of view, what is the most important property of the determinant, but surely one of the most important is the fact that determinant, usual determinant of product of two matrices factorizes in product of determinants. And this definition of superdeterminant again takes care of preserving this or extending this property from usual matrices to supermatrices, but you need to use this definition of superdeterminant. And basically, in order to prove it, one can use various ways, but the convenient way is first to verify, basically, that there is the same relation between superdeterminant and supertrace as between determinant and trace. Namely, that superdeterminant is equal to exponential of supertrace of logarithm of n. I assume n to be non-singular. In fact, why determinants play such an important role? In particular, they play an important role because Jacobians which appear when you change variables in integrals of many variables, they are Jacobians, they are just determinants. And in this capacity, they are very useful, in particular, not only in this, but in particular. And we shall see in the moment. I'll just formulate the statement which helps to change variables in superintegrals. In integrals, we know how the integration of anti-commuting variables is defined. As Martin says all the time, it's defined as differentiation. So there is no, in fact, difference between differentiation and integration over anti-commuting variables. But still, it's convenient in many cases to think this operation as integration, and then you can consider simultaneously integral going over several of these anti-commuting variables and simultaneously over several commuting variables. And you'd like to perform a general change of variables and to know how this integral, what operations should be done with integrand after performing such change of variables. And here I formulate a general rule which yes, please.
This formula relating superdeterminant supertrace is a logarithm nested?
Superdeterminant and supertrace. This is logarithm. No, just superdeterminant exponential of supertrace. No, I think it's correct. It's correct. If you take logarithm of both sides, that would log of superdeterminant is supertrace of log in this sense, if you'd like. But I prefer this exponential form. Okay, so how to change variables in the integrals? So involving both commuting and anti-commuting variables. So suppose we have such an integral of n commuting, okay, and just in fact one can consider also different number of, not equal number of commuting and anti-commuting, but here I just decided to take equal number of commuting and anti-commuting variables, and we integrate some function of all these variables, which I assume to be real. If I deal with complex one, always can consider separate integration over real and imaginary part. And we integrate over some domain D. Domain of integration has meaning only for commuting variables, of course, for usual variables. And we assume, in particular, that this function in the integrand vanishes when usual ordinary variables approach the boundary of the integration domain. So if this domain is infinity, then our function should decay sufficiently fast at infinity. If it's finite domain, I will assume that approaching the boundary, this function vanishes. Now, consider the change of variables. We replace our old variables with new variables y's and etas, and y's and y's are even elements, and etas are odd elements. So it means that etas are anti-commuting and y's are commuting. And so x is expressed as a function of these new variables, and also psi, our anti-commuting entries, are expressed as some function of new variables. Then Berezin proved that what one should do, you already may guess, that the role of Jacobian in usual variable change will be played by the corresponding superdeterminant, which is frequently called in the literature Berezinian. So what is this superdeterminant? It says that you should re-express, of course, it's usual thing. You re-express your integrand in terms of new variables, but you insert the factor of derivatives. So it's superdeterminant of supermatrix, which has, as any supermatrix, it has 4 blocks. These blocks contain commuting entries. These off-diagonal blocks contain anti-commuting entries, and they are obtained as corresponding derivatives. Here you take derivatives of every xi over corresponding yj, so it's n by n matrix of commuting entries. Here we have again n by n matrix of commuting entries, but we differentiate our old Grassmannians over new one, and corresponding anti-commuting entries are made of these derivatives. Now the integration domain is it's natural. It just goes over ordinary parts of new variables. It means over parts where we put all basically all Grassmannians to 0. These are ordinary parts. And integration goes over these new variables, Grassmann variables, ethers, and new commuting variables y.
Can I make a comment?
Yes, please.
Although the formula, the change of variable formula, looks very similar to the classical case, there is an important difference. And this is that in the classical case, you can consider making such a change of variables already in the absence of integration. You can consider the differential form or the density which you're integrating, and you can subject it to a coordinate change. You don't have to integrate to do that. And the transformation law is the same. You get the Jacobian. Differential forms or densities transformed by the Jacobian or the absolute value of the Jacobian. In the super case, this is not so. If you think that the integration form, which is also called the Berezin integration form, transforms by the superdeterminant, you're wrong. In fact, you can check. You just need to replace the differentials of the Grassmann variables, which are not differentials. You have to replace them by what they are, partial derivatives. Now, you know how to transform ordinary differentials. You also know how to transform the partial derivative with respect to a Grassmann variable. And you just sit down and work it out, and you find that the transformation law is not given by the superdeterminant. Superdeterminant is the leading law in a series of terms which you generate. And it so happens that when you integrate over a closed space, that all these correction terms, which come beyond the leading one, which is the superdeterminant, they integrate to 0 by something like Stokes theorem. So, in fact, for this to happen, in general, you need to strengthen the condition.
Vanishing of integral.
In Berezin, if you look at his statement of theorem,
No?
he requires not only that the function vanishes, he also requires that every single derivative up to infinite order vanishes at the boundary. He says the function should be compactly supported. In this case, you can never go wrong. Here, the special situation is that Jan has an equal number of commuting and anti-commuting variables, and that leads to some features which are more special than the general case. So, I'm not even sure it's correct, but maybe
I think
certainly in the situations of interest to us, it is correctly stated.
Okay. But we will use it only.
Question?
Yeah, please.
Yeah, just to make this clear with this change of domain, if I have a new commuting variable as a product of two anti-commuting variables,
No, you.
I wouldn't know now how to change the domain if I make something like that. Is this possible? That one of the new commuting variables is just a product of two anti-commuting before.
Yeah, this does not change the domain.
This just yeah.
The
Because you
domain
should.
is determined by the numerical part of the transformation. The fact that a commuting variable has an additive contribution from something that's even of second, fourth, sixth order in anti-commuting variables, it's not change the domain of integration. It just changes the integrand. You have to correctly recompute the integrand in the new variables.
But the domain will be the
And
same.
you need to correctly compute the superdeterminant of the Jacobian matrix. But that's the only thing you have to do. At the end of the day, when it comes to integrating, doing the usual integral, you just recompute the domain as you learned in school. There's nothing new here.
Yes, please.
Well, it's basically because everything is a formal series in powers of psi, and if you have an ordinary number bosonic field with a quadratic psi bar psi or something like that added to it, you just need a power series in that psi bar psi. So everything always remains coefficients which are functions of the bosons times lots of powers of psi, and you're always integrating over the same domains times the bosons.
Yes, precisely. Thank you for this comment. So, why we should bother about change of variables? First of all, because we really will use it in practice. So we should know how to do it. We will use it many times. And today I leave many simple but important facts as an exercise, because otherwise I won't progress much. But really show that by changing variables, you may verify the direct analog of Gaussian integral, so integral of exponential of quadratic form over supervector, where integration over supervector, I understand then product, just component-wise products of all components of vectors involved. And it's probably not a surprise to you that Gaussian integral, if it exists, and for this we should require that real part of this A, which enters here, and which governs, in fact, integration over usual commuting components, is positive in order to ensure convergence. If this integral exists, it equal to superdeterminant of inverse of M, or which is the same, which is pleasant, because superdeterminants they share all properties. I mean, all fundamental properties of usual determinants which make them useful. It's also inverse of superdeterminant of M. So now we know how to perform Gaussian integrations over supervectors, and we will use it in due course. Before, yes, please.
Why there is no condition on B?
Because look what this quadratic form tells you. Just substitute M, and you will see that B will be multiplied with only something made of product of two anti-commuting variables. Therefore, it's polynomial. So there is no. It's the same situation. Why, when considering Gaussian integrals over Grassmann vectors, we did not have any condition, because basically it's just expression for the polynomial. There is no property of being divergent Grassmann integral, just by definition. So that's why only we need condition on A. Now, we remember that in the heart of all our development was so-called Hubbard matrix form of Hubbard-Stratanovich transformation, which was at the bottom line was a Gaussian integral over matrices, over components of just Hermitian matrix, or maybe on a deformed manifold. So let us consider simple analog of this for 2 by 2. Okay, in fact, here consider general n by n case. So consider the following matrix Q, where this block is just Hermitian matrix made of usual commuting variables. Okay, I already used notation which will be very frequently used, and it's used all over in the literature. Namely, let me just fix this notation. I started to using it implicitly. It's so, for me, it's so natural. You see, if we deal with this block decomposition of supermatrix, where these are blocks, then there is a standard name in physical literature for those. And indeed, I think in all applications concerning random operators and random matrices and all that, I'm not sure that beyond that domain this notation is used, but I will use it heavily. Namely, we consider this decomposition in 4 blocks as naturally associated with this decomposition of supervector in 2 halves. First made of commuting variables, and second made of anti-commuting variables. Physicists think of commuting variables as something associated with bosons, and anti-commuting as something associated with fermions. And therefore, this type of decomposition is known as boson-fermion decomposition. Correspondingly, the names for these blocks are as follows. This corresponds to boson-boson situation. This is fermion-fermion, and product of 2 fermions is obviously boson. So this block is made of commuting object. And this block is boson-fermion, and this is fermion-boson. It was not written here explicitly, I just forgot it, but I already started using it. So please be aware of this notation. So if you look at this matrix, which I'd like to use for considering Gaussian integral over this matrix Q, which is analog of usual Gaussian integrals over, say, Hermitian matrices, you may note one curious difference. You may note this factor I in front of fermion-fermion block. And fermion-fermion block is, we consider it as Hermitian matrix. In fact, we will see that we will see in the moment that this I is not a misprint. It plays an important role. And how can we see it? Just by considering supertrace of Q squared. If you just calculate supertrace of Q squared using this rule for calculating supertrace, trace of A minus trace of B, you immediately will see that the expression is as follows. It's trace of Q of boson-boson block squared plus trace of Q fermion-fermion block squared plus part made of Grassmann.
Don't you need a minus sign in front of the mix, the Q trace?
Okay, well, let us check it. It depends, of course, on order in which you take this. But let us see whether we.
Oh, no, that's fine.
I think it's probably correct, but of course I could not remember. But it's important that if you change them, you will have minus sign. Okay, and you will see now the reason why this I is needed. Without this I would have minus here, and if I wanted to consider the most natural form most natural analog of Gaussian integrals over matrices of this sort, I would have a problem of convergence with respect to variables which appear here. With this choice of I in front, I do not have any problem of calculating this integral. By dq, I mean the product of differentials of all relevant entries in all blocks. In order to have one, you may check that one needs this numerical factor, which is of secondary importance to us, but just it's needed. And we will use this formula in its natural extension with linear term in the exponential to employ our old friend Haber-Stratonovich transformation. Now, again an exercise which will consist in 3 parts. Basically, by exercises, I mean some statements which I will use or make use of later on heavily, but it will be a distraction, and to prove them directly. And also they contain some useful, really, hints, and doing them you will acquire necessary skills of dealing with these operators. First is simple, verify, but this is very simple. This is just trivial thing. You just substitute here and you will see that it decomposes as usual, as for usual Gaussian integral of this sort of Hermitian matrices. This Gaussian integral just decomposes into product of Gaussian integrals with respect to each non-trivial degree of freedom and gives one. So this is trivial, much less trivial, but still do it. Restrict yourself to the simplest case of n equal 1, and remember n is size of each of these blocks, so it's 2 by 2 supermatrix, the simplest possible supermatrix which you may have of this form, and show that it can be diagonalized as follows. You can represent it in the following way: some supermatrix times diagonal supermatrix with entries which I denote QB and IQF. Mind the difference from these. These are BB and FF. Here is just B and F, and these are different objects. Then inverse of this matrix, and check explicitly that matrices V which involved in this diagonalization, they have the following structure. They have anti-commuting entry, they are supermatrices, so they must have anti-commuting entries here and here, and I denote the xi and eta. And in terms of the xi and eta, commuting entries are represented in this form, and explicitly in terms of our original entries, I give to you, for your convenience, just to verify, explicit expression for these xi's, etas, and also these eigenvalues, QB and IQF, or better to say diagonal entries, QB and QF, diagonal entries. First observation which you may make, that using using the properties of supertrace, obviously we can why cyclic permutation is so useful, because you immediately will see that supertrace, as for usual matrices, supertrace of Q will be supertrace of only diagonal part, because these two things will just cancel each other. And indeed, you may see that if you take QB minus IQF, you may see that these objects, these combinations will cancel away, and you will see that supertrace is, on one hand, is QB minus IQF, on the other hand, as it must be from the original definition, is QBB minus QFF. So everything is coordinated due to our definition of supertrace. However, this is not the end of exercise. Now exercise your new skill of computing Berezinians or super-Jacobians and calculate the associated change of Berezinian associated with this change of variables. You will find that it's just unitive. It's simple calculation using definition of this Berezinian, and you will find that it's unity. Then you will see that on one hand you have this integral which you already verified in step I, that it's 1. On the other hand, in new variables, it looks like the following. There is no Berezinian because it's 1. So, according to our rules, it looks like exponential of QB squared plus QF squared, perfect object, dQB dQF, very nice, and then goes integration over two Grassmann variables. And we know that integrations over Grassmann variables is equal to integral over Grassmann variable according to Berezin rule. I hope you remember. for any Grassmann variable, say eta, integral eta d eta equal to 1, integral d eta equal to 0. So you see that this will give you 0. So obviously your integral is 0.
Let me ask you,
Yes.
the QB and QF are the eigenvalues.
Yes. Explicitly, in terms of all things.
Well,
Okay, let us.
computation many times. I don't get a Palestinian as unity.
It's special. In fact, it's in Jacques' lectures. I took it from Jacques' lectures. It's a nice example. It's different. Yes, it's slightly different thing. You will see that it's as it shows in its unit. Because it's, you see, I make the following check. I go not to full. I calculate it from QB, QFF, QBF, QFB, not to xi's and etas, but still to xi's these sigmas. You see, it's only partial change. I think this is why you do not feel. But here it's even more clear-cut case because it's you have one. You can also have, in sense you know. But I like this because it's most clear-cut case of the paradox you encounter. So you have 0 and you have 1. 1 is equal to 0. So what is the problem here? Here it's already explained that in our way we perform the change of variable, which involved these two formulas, but those were not well defined when QBB equal to QFF and equal to 0, which is in our domain of integration. So we had a transformation which within our domain of integration was singular at some point. And so we obviously did something wrong because the result could not be simultaneously 1 and 0. And it's, I assure you, it's 1, it's not 0. How to tackle this problem? There are various ways. There is, in fact, general mathematical theory behind it. But I'd like to show you a simple way showing what's really happening. At least for me, I think it's instructive.
Do you mean that it's singular at QB and QF is 0? Or
Yes.
QBB? It looks more, I mean, I see over here.
Yes, QBB and QFF, they're 0.
Yeah, that's the singularity.
Yes, this is singularity.
Right, so
in our original domain.
Right. Okay.
Yes.
I've just, so you've written QB and QF is 0.
Oh, sorry. BB and FF. Here it's.
The numerical part is the same.
Yes.
In the light of the discussion we had
Yes.
earlier.
Important thing is the numerical part. Yes. But in fact, I think pedagogically even better to write here BB and FF in original. But yes, it's not that much difference in this. So let us see what's really happening here. We now understood that the problem arises due to this singularity. So let us try to exclude this singularity just by, say, considering a small ball around this origin and calculating our integral over the domain without this ball and then letting the radius of this ball tend into 0. Just consider the following step function, generalized function, which is 1 when it's argument positive and 0 when it's negative. So I just formally write the following integral. It's our integral, it should be obviously equal to limiting value when this regularized epsilon tends to 0 of our integral, original integrand, but with a part which explicitly prohibits QBB squared plus QFF squared being too close to 0, to this point which causes the problem. Now I make my change of variables. I know just from if I look here, you immediately see. In fact, it's also from expression here, just supertrace squared. In fact, so supertrace squared can be expressed on one hand in terms of original variables, it's like here, or it can be expressed in terms of QBs and QF, these diagonal entries. They're just the same, according to our transformation. So I can write down in new variables, because now I'd like to use new variables instead of BBs and FFs, Bs and Fs, but still all Grassmannian sigmas. So I just re-express my integrand. This is the rule, the prescription we had. Re-express your integrand in terms of new variables. So we are re-expressing it. But now we just notice that, okay, we have a function, okay, generalized function, but one can understand that one can expand with respect to these nilpotent parts and then get derivatives of this function, and derivative of step function is just Dirac delta function. So this allows us to perform this integral. Now we substitute this expansion. This is exact expansion because higher terms are just terminate due to the fact that squares of Grassmannians equal to 0. So we just take this object, substitute it back to the integrand, and now perform this problematic integration over Grassmannians, which was 0 because we didn't take care appropriately of this singularity, but now it will be non-zero precisely. Everywhere in our domain of integration it will be related with this derivative of theta function, which is delta function. And it's trivial exercise to see that the result of this integration for finite epsilon will be just exponential minus epsilon over 2, and it indeed tends to 1 as required when this regularizes tends to 0. So what is really the use of this exercise is just to remember that one should be extremely careful when performing change of variables in integrals involving both commuting and anti-commuting variables. Because if your change of variables is singular, you may have a serious problem. You may just do not have correct answer after doing this. And in fact, we shall see that these terms will appear in one part of our analysis. And in this topic, random matrix theory done by supermatrix calculation, or indeed further in applications to localization problems, these anomalous contributions which come from the, in fact, you may check that they come from, in some sense, from the boundary of always come from the boundary of integration domain. And these are known as, in the literature, as Yefetov-Wegener terms. Now we are really ready to evaluate the ratio of two characteristic polynomials that we are after. We assume in this calculation that imaginary part of the spectral parameter in the denominator is positive. We may assume that it's negative if we wish, but we assume that it's positive. Important thing that it's not 0. Then we represent, using the standard root, determinant in the numerator as Gaussian integral over anti-commuting variables, inverse determinant or determinant in the denominator as the Gaussian integral over usual commuting variables, and after that we have I use phi for vector containing usual commuting variables in the same notation as before. Psi for vectors with anti-commuting components. And we see that the problem of averaging over Gaussian distribution or GUE probability measure over matrices H amounts to calculating such averaging. And we know that this is a simple task because it will be exponential minus 1/2 trace of this object squared. It's easy to see, and just to check, that if one introduces the Euler matrix R, which as it must consist of it's 2 by 2 supermatrix consisting of 4 entries, and on the diagonal you have scalar product of phi with itself, and here it's minus scalar product of psi with itself. And here we have scalar products of psi with phi and phi with psi. Then please check that trace of a, okay, that basically this identity holds. And therefore, we in fact have.
Yeah. Isn't there an H on the right hand side missing somehow?
H? Where?
An H on the left hand side.
Yes. You average over H, so you have something which is H independent. It's 1 over 2n supertrace of R squared. So basically, we are now deal with integral of the following form. I write it for further comparison. 1, 1, okay, it's proportional to integral exponential I supertrace of matrix, okay, Z, ZB, ZF, 0, 0, times R, and minus 1 over 2n supertrace of R squared. R is made of phi's and psi's, and we should perform integration over these phi's. Okay, I will write it over supervector phi, over all phi's and psi's. So we need to calculate this. You remember, hopefully, that when we were in similar situation with product of only commuting, only positive powers of spectral determinants, only their inverses, we in both cases exploited two different methods, which in the end of the day they are related. We either used the fact that integrals whose integrals depend only on these on analog of this R, basically dependent only on this combination or only on that combination, can be very efficiently rewritten as integral over R itself. In the case of Grassmann variables, we call this trick Bosonization. And it had also counterpart polar decomposition, basically, or going to polar coordinates in the case of only this object. Here we can do the same, or alternatively, we used the Hubbard-Startonovich transformation, basically exponential of something squared. We linearized it, changed the order, and performed integration by now Gaussian integration over phi precisely. So these are two methods, and let us do both, but start. It's always in this context simpler to start with Hubbard-Startonovich transformation and then use it to verify Bosonization or super Bosonization in our case. So here everything goes very simply. We already know what is Gaussian integral, just standard Gaussian integral. We know it's equal to 1. If you shift it by linear term, you verify that it gives you precisely what you expected, exponential minus 1 divided by 2n supertrace of R squared, and substituted back here. So exponential of this term, replace it with such an integral, change the order of integration, and you will see, just notice that supertrace of q times R can be written down as quadratic form with respect to components of supervector phi, our friend supervector phi. That's why these supervector notations are so handy. We can write everything very compactly. And this matrix Q with subindex n is the following matrix. It's supermatrix, as it must be because it multiplies supervector. This supervector is of length total number of components is 2n, half of them commuting, half of them anti-commuting. So the corresponding decomposition of matrix Q. In this block, in all blocks, it has identity matrix, which of size n. I call it 1n. And here just this identity matrix multiplied with QBB, this entry, sigma BF here, sigma FB here, and I QFF there. So the problem amounts to calculating basically Gaussian integral. Now integral over phi can be performed because it's Gaussian integral of simple quadratic form, and we know how to perform it. It will give us inverse superdeterminant of this matrix, and because of this structure that it in all blocks is just proportional to identity matrix, the corresponding superdeterminant will be power of superdeterminant of basically this matrix itself, just consisting of these 4 entries. So it's written here. I also take into account these components here, which ensure convergence in particular. So we arrive to the following representation of our object in terms of integration over our set of matrices Q that we considered before. Okay, now one does standard rescaling, Q to square root of NQ. One gets n then as a factor in the exponential, and the corresponding expression can be analyzed by saddle point method. But this will go, basically this method is practically what, it's a variant, a very close variant of what was shown to us by Margarita. However, one can use this in the same way as we did for only integrals over involving commuting variables or only Grassmann variables. We can make step further and to prove analog of Bosonization formula, which in this case is known in the literature by the name of super-Bosonization. And in this particular context, one can verify the following useful formula, that provided that real part of the boson variable in matrix P, in 2 by 2 supermatrix P, is positive, the following identity holds, namely that exponential minus n supertrace of this matrix P of this form times matrix M times superdeterminant of M raised to power n integrated over M, where M has special structure, namely its boson variable is positive definite, its fermion variable is unimodular, and alphas and betas are just Grassmannians, and provided n is larger or equal than 1, this identity holds. You may just, for these 2 by 2 matrices, it's easy to verify just by direct calculation that it holds. In our particular case, for our particular problem, let us look here. This is our matrix P. Due to the choice of sign of ZB that we have been doing from the very beginning, that imaginary part of ZB is positive, you may immediately check that that indeed this matrix satisfies the condition real part of this object is positive. And therefore we can just exploit this identity. We substitute it back. We perform explicit, now it's very easy to perform Gaussian integral over Q. And we come to the following formula, re-expressing our object of interest as this time integral over supermatrices M with these properties. And now compare this formula, that's why I wanted to have it on the board written. This formula with that formula. You see that basically we have the following identity, which this particular case can be just generalized to a general case, and this is precisely this superpositionization identity, that if you have an integral whose integrand depends only on this matrix R taken in this form, then performing integration over components of supervector phi amounts to just replacing R everywhere with M given above and inserting the factor superdeterminant of M to N. So this is in fact general superpositionization identity which one can use here. And let us analyze our density, our object. Let us perform briefly saddle point analysis using.
Maybe we can once again and then for the last time discuss this identity.
Okay.
So the general philosophy is that when you do an integral and the integrand depends only on some invariance, so it doesn't have all the possible dependencies, it just depends on a certain set of variables, then of course you would very much like to introduce these variables as new variables for integration. And so you hope that you can do this, and if you can do it, then you expect to pick up in the integrand an additional factor which measures the volume. So you have invariant surfaces along which the function is constant. Hopefully these invariant surfaces are compact or measurable in some sense, and you can associate with them some volume or area. And then the new integral will have an additional factor which sort of measures these volumes of the invariant surfaces. The simplest example of this is known to you. It's introducing polar coordinates in the plane when you introduce a function that has rotational invariance. Then the invariant surfaces are the circles. And what appears in the polar integral is R, the R, because R is the circumference, 2 pi times R is the circumference of the circle of radius R. So this idea, which is known to everyone here and is useful in many contexts, turns out to work in the super context. It's not obvious that such a thing is possible in the super world, but
especially, may I make a comment? Especially,
it is, and somehow the super determinant of M is the analog of R. It measures sort of the volume of these surfaces along which the integrand is constant.
Yes, precisely. But just to show that it's not that trivial, the idea is precisely like Martin described. But this we already encountered that for Grassmann variables. My comment is because you, Martin, said that you just hope that making these matrices variables of integration will help. In essence, this what happens, but non-trivial part that this block, or this, in our case, this nilpotent commuting number is just replaced by integration over unitary circle, which is far from being obvious when looking at this object. Yeah. So it's not that simple, but it's on this spirit.
Yeah. So there was a question by Christian Sadl earlier who said, what do we do when our commuting variables have shifts by even nilpotent? And the answer was nothing, it doesn't affect it. So now we're taking this back a little bit. It's context. Something that's even in just that has no numerical part, and it just consists of degree 2, 4, no degree 0 part. Degree 2 and possibly higher is converted into an integration over some kind of a circle or something.
So
and that's non-trivial. This needs to be proved. And the idea behind it is that this integration over a circle is computing a residue. And as such, it is computing some order of derivative. But that is what Grassmann integration does. It's taking derivatives. So there's more than one way of computing a derivative.
Yes. Okay, let us, with all these due comments, let us go forward. So let us perform this. I just give all important ingredients of this calculation. You may then just check it. It's easy to calculate super trace of m squared. Just multiply m with itself and take difference of diagonal elements. After that, you will get this. It's also easy for 2 by 2 matrices to calculate superdeterminant according to either this or its counterpart formula. Anyway, you may check you will have this expression. And now you substitute it into the integrand. You remember that, you try to remember that you had two spectral parameters. In the numerator you had z plus t, in the denominator you have z, but now we are going to perform large n limit or investigate large n asymptotic of this, and we should remember the goal for which we wanted to calculate it. We wanted in the end differentiate over t and set t to 0. So when calculating this limit, it's just, you may consider t to be arbitrarily small, if you like. And this just helps in evaluating this limit. So also, in the end of the day, we'd like to set imaginary part of z to 0, because this limit should provide us with spectral density. So having all this in mind, we see that we have just one integral going over these variables MBB. They are positive definite. Integral goes from 0, they are just positive, it's just one variable. So it goes from 0 to infinity. You have this unimodular integration over unit circle in complex plane over variable MFF. You have exponential minus a big factor n and multiplying L, this LB here, the function of MBB. You have large factor n multiplying function, it turns out to be precisely the same function, but of variable MFF, of unimodular variable here. And also you have this factor depending on also on both MBB and MFF, and it's written here. As I mentioned, we are interested in n going to infinity, t going to 0, but in the end we should put t equal to 0. So when calculating large n limit, I just may assume nt finite and do not consider this factor as contributing to changing saddle point. Then saddle points are just the points where derivative of this function is equal to 0, and you immediately get quadratic equations which you solve, assuming that modulus of z is smaller than 2. You solve and you see that these are expressions for MBB and MFF at these saddle points. You also need second derivative of these functions L and LB and LF, which are the same as functions, because this will define basically your Gaussian integrations around saddle points. And you see that for MBB you have only one saddle point in the relevant domain of integration, but you may have two of them with plus, depending on plus or minus sign, both are allowed when you consider this integral. However, now, as we already encountered in other examples, pre-exponential term play important role. Namely, we see that for one choice, when MBB is not equal to MFF, actually here we always have plus sign, but say here we have minus sign. Consider product of the two, you will see that it's equal to -1. Then we see that precisely at this saddle point, pre-exponential factor vanishes. And clear, this will result in contribution from this particular saddle point, although could be taken into account. It's just of the smaller order in parameter 1 over n. Therefore, dominant contribution comes just from the choice when plus here and plus here comes simultaneously, and we immediately obtain expression for which is written here, and differentiating over t and putting t to 0, we recover semicircular law. So this is how semicircular law appears in this way of calculation, and we already know how it appears in a complementary way. So now you have two different perspectives. Please.
Can you describe again why MBB has only one value?
Because you integrate. from 0 to infinity. So you should, if you have MBB negative real part, then you should deform. You will see that you cannot deform contour appropriately in order to for this saddle point to contribute. But it's completely clear that if you integrate from 0 to infinity, you should take this. Okay, let us leave it here. Now,
Sorry.
yes, please.
So it seems MBB is sort of an analog of the single site variances, right?
Variances.
So because if you differentiate with respect to t, you're going to end up with an MBB downstairs, and this when you integrate over it.
I would not say this because you could, you see, I just make a choice to have this t in the numerator. I may have it in denominator, then it probably will be slightly
So
different.
the t, you
I should, I could not, but I do not see that it has immediately this interpretation. I don't think that it has.
Well, we saw an identity where we had this integral, and then we had extra factors. We were integrating over the products of phi and phi
Yes.
transpose, right? And in this case, MBB would drop out of that.
Well, MBB is just, you see, it's. I should stress that both bosonic and fermionic. It's not correct to think that they play plays dominant role and second plays just auxiliary role. In some sense, it's not correct. They are all relevant.
I guess what I'm asking, are these just algebraic things that drop out, or do they have some sort of physical interpretation?
At this level, no, I don't think that. I don't think that you may interpret them on this level.
Okay.
No, I don't think. At least I do not see. Do you see any?
As we see at the saddle point, MBB coincides with what
Green
physics call the
function,
Green's
yes.
function,
Green
and
function,
what
yes.
Leonid Pasteur called the Stiltes transform of
Yeah.
the counting.
But its expectation value at saddle point, not itself MBB, but just its expectation value at saddle point, it gives you trace of green function. If it helps, I don't know. I don't think that it's very physical interpretation.
I would like to remark that the second saddle will enter if you start taking derivatives in energy of the Green's function. In other words, you look at the average Green's function on the diagonal, take a derivative, then you cannot ignore this other term. In fact, it's quite large. And
The
you will
reason is that it gives strongly oscillate, so that this density is very smooth.
right.
In fact, in the local scaling limit, it's just constant.
Yep.
While this other term is highly oscillatory, and so when you differentiate, you're killing this term, and the other one is enhanced. So Tom is exactly right.
That's in fact that's why, without going into detail, I mentioned that it's not correct point of view, which some people mention sometimes, that this fermionic block plays auxiliary role. It's not correct. They both coherently play important roles in producing correct structure of green functions, of expectations of green functions, and their product in more complicated cases. Okay, now I still have 10 minutes, so maybe very briefly, I just show, it's not much more difficult, just one.
Well, we don't want to run overtime because we're going to take the workshop.
We won't go overtime. I just show basically that precisely the same structure, just last for today, precisely the same structure is extended without any problem, just directly the same calculation extends to general, and we will calculate particular case of the general correlation function, which I think it's interesting. We'll just calculate it next time, explicitly. But the scheme of coming to a super bosonized version, converting or expressing this this object, complicated object, arbitrary number of determinants with different, possibly different spectral parameters in the numerator, then the product in the denominator with yet different z's, and following just step by step, precisely the same procedure without any modification, one very easily arrives to the expression, which of course one should analyze further in the large n limit, and we will do it in slightly different fashion. But let us in a few minutes go through it. So we express individually every determinant in the numerator as its own a Gaussian integral over its own vector made of anti-commuting components. In the same way, every determinant in the denominator expressed as its own integral over complex vector of usual vector with commuting components. Then you need to perform ensemble average of something which has always this nice form, exponential trace h times some matrix. This is a matrix. And it will be equal the result of this average exponential minus 1 divided by 2n super, first will be trace of this matrix squared, and then just by previous example you notice that introducing convenient notations, just matrix Z for diagonal matrix, which diagonal supermatrix, which has ZBs, all these ZBs in this block, and all these ZFs as diagonal entries in fermion block. Then introducing also matrix made of signs of ZBs. We remember these signs play very important role, and we keep them. So we introduce matrix S, supermatrix S, which has identical matrices in fermion and in boson fermion blocks, and it made of this plus and minus 1 depending on sign of individual ZB. And we also introduce supermatrix R, which is made of this combination that we already know. We know this combination very well. It was used in our calculation of only negative moment. That's why, in fact, we did it first, because we know all the structures. We know this matrix. It appeared when we calculated only products of determinants. Here, naturally, appears just mixed matrices made of products of matrix made of Grassmannian vectors with corresponding matrix made of usual complex vectors. And here appears its counterpart. And in terms of this object, we come first, we notice that the result of this averaging can be written down in very compact form, in this way. And now we use, we should still prove it, but one can use for as long as capital N is smaller, is larger or equal than number of these determinants in the product, one can convert it to the super bosonized version of a matrix M, which just generalizes this simple 2 by 2 case, but has all the same properties, namely, it's positive definite in boson-boson block. It's matrix of n by n Grassmannians here and here, but for MFF, not surprisingly, you have just unimodular matrices or unitary matrices of size n. And for the measure, you have just generalization of what is written here. You should take into account determinant of this unitary matrix raised to power n, and integrate here over Haar measure on group of UN. And this is really the form which can be used for further extracting asymptotics in large n limit. But this will be done next time. Thank you.
Going back to what Ben said, is it not MBB in the previous cases, like a boson bilinear? And so you differentiate with respect to T expectation value to both.
you will again, but answer is precisely like that, that at certain point, we will see first of all, that depending on particular signature here of matrix S, if S is proportional to unity matrix, then all analysis practically goes parallel to this. If it's
I'm talking about this case, previous case, just with.
okay, if it's trivial case, it will be basically just repetition of this analysis. MB will get will be proportional to green expectation of green function at saddle point, and that's it. So in this sense, it will be the same. But it will be much more complicated, as we remember. It must be like that. If S is has minus 1 structure, because then it will have these sigma model-like modes. So it will be the whole integration saddle point manifold rather than just isolated point. And this we will see next time.
So now we're going to have a picture. Everybody who wants to be in the picture, and I hope that will be everybody, please follow Stephen out into the patio. And